Students, this is lesson U5A05b. By the end of the lesson, you should be able to say, I can apply sine, cosine, tangent to solve for sides of a given triangle. So, students, in the past lesson, we looked at the derivation of the Pythagorean theorem, and which then allowed us to work with right triangles specifically. And in the last lesson, we were able to solve for side lengths of similar right triangles that were of 30, 60, 90 or 45, 45, 90. So what I'm going to talk about in this lesson is, we can still solve for sides of a triangle if we were given not just two sides of a right triangle, but if we were given one side only. Now, in order for us to do this, we have to be given another piece of information, and that is we need to be given an angle, And this angle here is really important. If you recall from the Pythagorean theorem, we had a squared plus b squared is equal to c squared. Notice that there is no distinction between what a and b is, other than that we have two different legs, right? But there is no distinction as to which leg are we referring to. We can call any leg of a right triangle a, and we call the other leg b, and the Pythagorean theorem would still work if the dedication were to be put in reverse. So what's different in this lesson is now I'm introducing an angle here, and with the introduction of that angle, now we have something to reference with. So a here, this side length, in reference to this angle, it's going to be opposite of that angle, and b here will be adjacent to the angle. Same thing could be said about this larger right triangle over here. This d is opposite of angle theta, and e is adjacent to angle theta. And also, my apologies for not saying this to start with, this symbol right here, let me use a thicker marker, this symbol right here is a Greek symbol. This is theta. And it's treating what theta is, it's describing an unknown angle. So it's no different from the letter x or the letter y, or calling any old angle by any name. It's no different, However, in many textbooks, as well as in future math courses, this symbol is widely accepted as used to represent an unknown angle, So anyway, a here is opposite of theta, b is adjacent to, d is opposite of theta, and e is adjacent to. All right, so with that in mind, this gives us a little more, some more to play with, in our ability to communicate. So what we can do with this, is, yes, legs A and D are going to be opposite of theta. I encourage you to write that down so that you can understand what I mean when I say it's a side length that's opposite to. Again, when you're opposite of something, you're facing that object. Legs B and E, they're adjacent to theta. And then, of course, sides C and F, they're the hypotenuse of the right triangle. With this understanding, because these two triangles are similar, I can then perform the following ratios. I can say that A over C, the opposite leg over the hypotenuse, will be equivalent to the opposite leg over the hypotenuse. These two triangles are similar, because of angle-angle theorem. Once again, we have an angle, an angle, an angle, and an angle. So, for better communication purposes, this ratio here, because it comes up all the time in mathematics, the ratio for opposite over hypotenuse is what we call a sine ratio. This is a sine ratio. So the sine ratio is opposite to hypotenuse. So if we say, what's the sine ratio of a given right triangle? You're going to take the opposite side length of the angle that we're observing and divide it by the hypotenuse. Then the next ratio we have is B over C, okay? So B is the adjacent side, and C is the hypotenuse. We refer to this as the cosine ratio. And this is adjacent over hypotenuse once again. The last ratio, okay, that we're going to talk about is A over B, which is opposite over adjacent. Opposite over adjacent is equal to D over E, which is again equal to opposite over adjacent. These are all similar triangles. We can set up these similar proportions. This ratio has a name. We call this the tangent ratio. And again, this is opposite to adjacent. These ratios are applicable only for right triangles only. And again, emphasis here, this is only applicable for right triangles. Anytime that you're not dealing with a right triangle, then these ratios do not apply. Okay, so different values of theta will produce different ratios. So with that in mind, okay, depending upon what the value of the angle is, we're going to produce different ratios as a result of this. So for instance, if I have a triangle with an angle of 10 degrees here, okay, that's going to produce for me a ratio between the opposite side to the adjacent side. So just upon inspection here, do you expect a large ratio or a small ratio based upon the way that this diagram here looks? Again, we have a opposite to the adjacent here, right? So if you're thinking it's going to be a small ratio, you're absolutely right. That's because this side length here looks significantly smaller than this guy right here. We expect tangent of 10 degrees to be something very small. Sine of 20 degrees, okay? Sine of 20 degrees, I have 20 degrees here. And then sine of 20 degrees means, again, the ratio between opposite to the hypotenuse. So, what does that mean? Well, here, this is the opposite side, and this is the hypotenuse here. We're expecting a ratio of opposite and hypotenuse, okay, of this 20, 90, 70 degree triangle. So again, this is going to be a small ratio again. It's going to be something small. We expect it to be less than 1. Similarly with cosine of 50 degrees, if I have adjacent to hypotenuse, this is what I'm asking for here is what is the ratio between the adjacent and the hypotenuse of a 50, 90, 40 triangle. So again, we expect that ratio to be something small. We expect it to be less than 1 because we can see that the ratio of the adjacent side is smaller than that of the hypotenuse. All right. We actually came up with these side lengths here in the previous video. If you recall, if you don't remember this, I encourage you to go back and look at U5A05a, okay, and take a look at how these side lengths came about. So according to what was discussed, okay, in the beginning of this video, let's try to find out what are all these different values here. So if I have sine of 30 degrees, okay, sine of 30 degrees, so I'm looking at this triangle because this is the only triangle that involves 30, right? So I want to take sine of 30 degrees, and what that means is I want to take the opposite of 30 and divide it by the hypotenuse. As a result of this, what I'm going to end up with is 1/2. If I take cosine of 30 degrees, okay, so cosine of 30 degrees, that's adjacent to the hypotenuse. What I'll end up with is radical 3 over 2. And what I'm going to do next is I'm going to take tangent of 30, and that is opposite over adjacent. So that's 1 over radical 3. And as I've discussed in the previous video, we do not leave radicals in the denominator. What we have to do, we have to rationalize this. So we're going to multiply both the numerator and denominator by radical 3 over radical 3. And the result is radical 3 over 3. Pause the video to see if you can figure out the rest of these trig ratios. Hopefully you guys had some time to think about this. Sine 45, okay, cosine 45 and tangent 45. Well, sine 45 sine 45 and cosine 45 are the same thing. They're going to be radical 2 over 2. Tangent 45, as it turns out, is equal to 1. That's because the ratio of opposite to adjacent is the same, right? And then we have sine 60, cosine 60, and tangent 60. The result is going to look very, very similar to the first column that we have here. So sine 60 is radical 3 over 2, cosine 60 is 1/2, and tangent 60 is radical 3. Again, the ratio of sides of a right triangle are commonly referred to as trigonometric ratios. So these, okay, are what we refer to as trigonometric ratios. Do you see in this word here, even though it looks really complicated and scary, right? There's a word here, trig, right? So trig, okay, that prefix just implies triangle. So what we're doing here is we are talking about the ratio of sides of triangles. Let's try to apply this concept to finding out the missing side lengths in this triangle here. If I'm trying to solve for side length x and side length z, what I have to do is, well, I have, let's say I'm trying to find out what x is first, okay? So I'm trying to find out what this is. So x right now, and I know that this is 60 degrees here, x right now is adjacent to 60 degrees. Which trig ratio, sine, cosine, or tangent, will involve 12, which is opposite of 60, and an adjacent side? If you're thinking of tangent, then you're absolutely right. So what we say then is, we say tangent of 60 is equal to opposite over adjacent. And then we solve for x. But wait a minute, don't we know what tangent of 60 is? Tangent 60 is radical 3, right? So again, this information over here is super important and super helpful. Actually, when you move on to advanced algebra or algebra 2, okay, it is encouraged that you have these trig ratios memorized. I'm going to encourage you to start memorizing this through practice. I don't want you to create index cards and just try to memorize this verbatim, okay? But I want you to memorize this through practice and through exercises. So anyway, we're going to solve for x. So when we solve for x, we'll end up with 12 over radical 3. And we're going to rationalize this. This turns into 12 radical 3 over 3. Or really, it's just 4 radical 3. And then similarly, we can solve for z. Now, if we solve for z, okay, looking at this, 12 again is opposite of 60, and z is the hypotenuse. Which ratio will have opposite to hypotenuse? Well, that's just sine. Sine of 60 is equal to 12 over z. And what exactly is sine 60? Well, sine 60 is equal to radical 3 over 2. So therefore, now I can solve for z. So to solve for z, I'm going to cross multiply. I end up with 24 is equal to z radical 3. And then dividing both sides by radical 3, I'll end up with z is equal to 24 over radical 3. And then I got to rationalize. So I want to multiply both the numerator and denominator by radical 3. I end up with 24 radical 3 over 3, which then becomes 8 radical 3. Let's take a look at another example. So we're going to find out what side length P and Q are. So P right now I immediately see, okay? Or actually pause the video to see if you can give this a shot on your own, okay? So hopefully you guys had some time to think about this, okay? So upon inspection here, I immediately notice that 15 is the adjacent side and 15 is the adjacent side to 30 degrees. P is opposite of 30 and Q is the hypotenuse. So being able to identify which side is opposite, which side is adjacent, which side is the hypotenuse is really important for your ability to interpret whether to use sine, cosine, or tangent. So looking at this, I know that if I were to solve for Q, okay, I would have to involve 15 here. 15 and Q, 15 is adjacent and Q is hypotenuse, therefore I would have to use cosine. So what exactly is cosine of 30? Well, cosine of 30 is radical 3 over 2. Now then I can cross multiply. and divide by radical 3, I end up with 30 over radical 3. But again, I got to rationalize. So therefore, I end up with 30 radical 3 over 3, or 10 radical 3. I again want to solve for what p is. So here I'm going to apply tangent, because I know p is opposite of 30 and 15 is adjacent to 30 degrees. So therefore, the ratio will be opposite to adjacent. Tangent of 30 degrees is radical 3 over 3. Again, I would cross multiply. So I end up with 5 radical 3 as the side length for p. Let's do another example. So immediately upon inspection, I already know that this both a and b will, well, actually, pause the video, see if you can figure this out. Upon inspection, I already know that a and b are going to be the same value, because we're actually dealing with an isosceles right triangle here. We have 45, 45, 90. So, therefore, it really doesn't matter whether we use sine or cosine, okay, to find out what a is. But I do know that a is opposite of 45, and b is adjacent to 45, and 10 is the hypotenuse. So therefore, I am going to use sine 45. And again, it doesn't matter whether we use sine or cosine, we end up in the same place. We have radical 2 over 2 is equal to a over 10, because that's what sine 45 was equal to. I multiply both sides by 10, and I end up with a is equal to 5 radical 2, or b is also equal to 5 radical 2.